Hi, welcome back to Physics on the Internet. So this is, I think it's what chapter is it? Chapter 9 in the physics book, but this deals with the homework on collision problems. So if you're having issues with figuring out how to do those collision problems, maybe this will help. First of all, pause the video, zoom in, and look at this problem. Okay, so here's the deal. Conservation of momentum, like any other conservation problem, the only thing you have to worry about is the before and the after. And the collision problems that we do are all in a straight line, and we assume that it is a closed system. So what that means is we don't lose any mass. The system are the two objects that are going to interact in a linear fashion, and we're not going to lose any mass to the environment or anywhere else. It's just all going to be contained within that system. So there are three types of collisions. There's actually just two. There's inelastic and elastic. And we talked about these in class. You can refer to the PowerPoint if you have issues with the definitions, but all of them are going to help us, the definitions, set up the problems. So this problem's on the board, we need to look at it, and it's the key to success on these problems is the labeling. So you're gonna have two objects. I call them A and B. You can call them 1 and 2 or X and Y, whatever you wanna do, but I'm calling them A and B. And so if you read this problem, you have a rubber bullet. I'm calling that A. So the mass of the rubber bullet is 12 grams. And right away, that's problematic because we need to have these things in kilograms. So divide by 1,000 and you've got your kilograms. So your little rubber bullet has an initial velocity. It does have an initial velocity. I'm gonna draw the picture over here. So you're gonna have this little rubber bullet and then you have a concrete block. And so I'm gonna call the rubber bullet A and the concrete block B. And they tell me the mass of the concrete block is 8.5 kilograms. So there's your A and B. And the concrete block is just sitting there to start out with. And the rubber bullet is going to hit the concrete block, and then it's moving, it says, to the right, and the concrete block is just sitting there. And then the rubber bullet collides with the concrete block, which magically is on a frictionless surface. And the rubber bullet is going to ricochet, and you have to know what that word means. It means to bounce off and go in the opposite direction. And after the collision, and the concrete block apparently is going to move. Now, you can guess, I'm going to guess that it's probably going to move to the right, but if you don't know, it's okay, because if you guess incorrectly, the sign will be wrong, and then you can change it, but it'll be fine. So you've got your A and B. The initial equation that we start out with is always the same for every single problem. So you have the initial and you have the final, and I'm going to adjust the camera just a little bit so we can see the rest of this stupid whiteboard. There we go. And now it's at a weird angle, but we'll do the best we can. So all of the, and then I'll frame this up when we're done. All of the equations, all of the problems start out with the same equation. Some things cancel out, some things will combine, but it's that the initial momentum equals the final momentum. That's what conservation means. So we have momentum for the first object. It has a certain amount of instantaneous momentum before the collision. And then we have the second object, same thing. Because the definition of momentum is that it's the product of the mass and the velocity. And remember, velocity is a vector, so signs are important. And then we have afterwards. They have to be equal to one another. So we have the momentum afterwards of the first object and the momentum afterwards of the second object. And the thing that changed is the velocity. The mass is not going to change. We're pretending that bits of the bullet are not breaking up. It maintains its mass. The velocity is what changes. So then we have to think and go back to our problem. The rubber bullet does have an initial velocity. The initial velocity of the rubber bullet is positive because it's to the right. That goes back to everything that we've done, and it's 150 meters per second. The initial velocity of the concrete block is 0. Well, if the velocity is 0, that means the momentum is 0. So this entire factor of our equation is going to cancel out. So that's nice. And then it says afterward, the final velocity of the bullet is negative 110 meters per second because it ricocheted. And they didn't have to give you that negative. They just did that to be nice. I won't always be nice. So ricochet means it's going in the opposite direction. If you refer back to the picture that I drew at the beginning of this, ricochet, it's going to the left, and left is negative, and that's why it's a negative 110. And they want to know what's the velocity of the concrete block. What's the velocity of the concrete block when this is all over? So I know this, I know that, I know this and this, I know that. I don't know this. And this is the only part that now is not physics anymore. This is algebra. You have to rearrange the equation and solve for the final velocity of the concrete block. So these are being added. I subtract from both sides. So I'm going to have MA VA initial minus MA VA final. And that's going to equal the mass of B times the final velocity of B. I subtracted this quantity from both sides. Now I need to get rid of the mass of the concrete block. I want the final velocity of the concrete block to be by itself, so I divide both sides. And now I know how to get the final velocity of the concrete block. I take the mass of the bullet times the initial velocity, which is positive, and I need to keep it that way. And I subtract from that mass of the bullet again, 0.012 kilograms, and it's negative 110 meters per second. That's important. You have to keep that like that. And you divide that by the mass of the concrete block. Kilograms will all cancel out, leaving you with meters per second. Remember, you have to cancel it out from each factor, and then you just do math. Remember, this is minus, and this is a negative, so technically you're going to add that second product. So it's going to be 0.012 times 150, and then you're adding the product of 0.012 and 110. Dividing by the concrete block, you get 0.37. So the concrete block, it's positive, 0.37 meters per second. It should be small, it's a concrete block. It's very heavy. So what does this mean? It's going to go 0.37 meters per second to the right. And this is just right after the collision happens. And that's how you do every single one of these problems. The key is figuring out how to label. It's not, every problem is not exactly the same because they're going to give you different information. Sometimes nothing cancels out. Sometimes the two are going to be in an inelastic collision and they're going to share the same final velocity. That's how you do these problems. I hope that helped.